Welcome to the vodcast for section 9.7, functions of a random variable. It is March 15th, 2011, and we're going to talk about these functions of a random variable. Now, functions of a random variable implies that we're talking about functions. For example, we might talk about p of x, and what we would mean by this is x is the number of times we're interested in something occurring, and we want to know what the probability of that is. And we'll have a formula for that, just like we've had equations for functions in the past where you can plug in an x value and get out a probability. We'll talk more about what those equations will look like later. Most of these functions of random variables that we'll talk about will primarily be talking about binomial probability functions, and we'll talk about binomial probability distribution. Now, as binomial implies two things. For example, it could be heads, tails, could be stop, go, could be brown hair, not brown hair, but it can't be something like brown hair, black hair, blonde hair, purple hair, because that's more than two things. We're only talking about binomial things that happen binomial, and these binomial possibilities of things happening are mutually exclusive. They add up to 1. So if the probability that I get a heads on a bent coin is 60%, the probability that I get a tails is 40%, those add up to 100%, or 0.4 plus 0.6 equals 1. So x could be the number of times, let's use this example, number of times that you stop at a light when you're driving through town and there's 5 lights you have to go through on your way to school every day. Okay, so on your trip, 5 lights on your trip. And you do this every day, and you want to see what it seems like you're stopping a lot. So let's say the probability of, and all these lights are kind of set the same way, but the probability of stopping is equal to, let's say you've got a 40% chance of stopping. That means that the probability of not stopping, let's call that go, is equal to 0.6. Okay. So we might think about what is P of 3? P of 3 would be counting the number of times you stop 3 times. What's the probability of all the things that can happen? What's the probability of stopping 3 times? Now that means you could stop at the first 3 lights and go through the last 2, or you could go through the first 2 and stop at the last 3, or all kinds of possibilities. So we could say, now one way we could figure this out, some of this out, is we could draw a big old tree diagram. So here's what the tree, just to review a little bit, here's what the tree diagram might look like. We could stop or go at a light. From this light, if we stop at the first light, we could stop at the second light, or go through the second light. If we go through the first light, we could stop at the second light and go through the second light, and keep on going with this tree diagram. We do not want to write out this entire tree diagram. But one thing we remember from this tree diagram is we could figure out like how many different things could happen in this. In other words, what is the total sample space of this thing? Well, it would be, since it's binomial, it would be 2 times 2 times 2 times 2 times 2. It would be 2 to the 5th. There'd be 2 to the 5th different things in this sample space. Okay. Well, one possibility would be, like we went through this tree diagram, one possibility would be S, 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 go, go. Another one would be S, go, go, S, S, etc. This kind of reminds me of when we were doing words like bubbles and freely and things like that, and we came up with this idea that the number of ways that all this could be arranged, the different words, would be 5 factorial divided by 3 factorial times 2 factorial, which happens to be exactly the same thing as 5c3, which is equal to 10. Okay, so we have this number out here in front, 10. Now, the probability of one of these things happening, let's see, would be 0.6 times 0.6 times 0.6 times 0.4 times 0.4. That's what the probability would be for that exact arrangement, the SSSGG. How many of those things are there? Well, there's 10 of those things. So if I did that for every one, for the one below it, it would be 0.4. Move this. The one below it would be 0.6 times 0.4 times 0.4 times 0.6 times 0.6. I could write all of these things out from the tree diagram or just from some systematic way of listing all these things. I'd have all 10 of them. Each one, though, would have 3 0.6's multiplied together and 2 0.4's multiplied together, maybe in different orders, but they would all come out to be the same. They would all come out to be 0.6 cubed times 0.4 squared. Okay, and I calculate that out. In fact, let's do that on the calculator, see if I can get this calculator to work. There it is. Hopefully this works. I could do this on the calculator. In fact, I'll do it with the combinations. I would do 5 math probability C, what did we do in here? C3 times 0.6, oops, 0.6 cubed times 0.4 squared. That is what this turns out to be, 0.3456. What a nice number. Rid of that. This equals 0.3456. So that is how I would calculate it for that particular thing. Now let's look at sort of the general idea, the general formula for this whole thing as we move down here. The probability distribution function looks like this. P of x is equal to NCx, where times a to the n minus x times b to the x. What do these things all mean? Where x is the number of times an event happens in n repetitions. So we were just counting how many times we stop. So x was standing for the number of times we stop, and it was 3 in our example. And n was 5 because we had 5 stoplights to go through. And b is the probability that the event occurs in a single repetition. In other words, I have the same probability of stopping each time, and it was 0.6. Ooh, I did that backwards. Darn. We'll switch 0.6 and we'll just switch 0.6 and 0.4 around up here, and that'll make everything work out. I hope I'm not confusing you too much. This is 0.6 and this is 0.4. Good thing I'm paying attention. Okay, So B is the probability that the event occurs in a single repetition. This was 0.6 in our example. And A, A is the probability that it doesn't occur, which in our case that meant if you didn't stop, you go, and that was zero point 0.4 in our example. Okay, so we can write this. We're actually writing this as a function. We could then put values into this function like this. What's P of 2? P of 2 would be 5C2 times A was 0.4, so 0.4 to the 5 minus 2, which is 3, times 0.6 squared. And I would calculate that out. Now, what a probability distribution means is that you figure out all of these things. What is P of? Well, what can happen? I can stop 0 times. I can stop 1 time. I can stop 2 times. I can stop 3 times, 4 times, 5 times. This doesn't include getting stopped by a policeman because you're speeding or any kind of other stops, just the stoplights. That's all we're talking about here. But I can figure out the probability distribution for this whole thing. Now this would be 5C0 and 5C1 and 5C2 and 5C3 and 5C4 and 5C5. And I think we had a problem the other day where we counted up, in fact, with 5, all the different combinations, and it turned out to be 32. And that's what we found out when I was talking about the tree diagram above. That's all the possibilities. And what should all these probabilities add up to? This is all the stuff that can happen. What do you think? Think about it. This should add up to 1. So you should be always checking your probability distributions to make sure that they do add up to 1. So this is the probability that I stop 0 times. So that means that that's 0.4 to the 5th, 0.6 to the 0, which is of course 1. Multiply those things out. 0.4 to the 4th, 0.6, I get stopped once. 0.4 cubed, 0.6 squared, 0.4 squared, 0.6 cubed, 0.4 the first, 0.6 to the 4th, and 0.4 to the 0, which is again 1, times 0.6 to the 5th, which means I get stopped 5 times. Now on your calculator, there's some kind of nice, as you might suspect, cool ways to calculate that without having to go through the whole business. One thing we can do is we can do it with lists. Let me show you how to do that. Go to your stat menu, go over to lists. I want to put in my X values, which are 0, 1, 2, 3, 4, and 5. Then I want to write the function in L2. Okay, here's how this works. There's some easier ways to do this on your calculator, but I want you to pay attention to the actual formula and put it in this way. So we put in 5, that's the number of repetitions. Then we do math probability NCR. Now, NCR of what? Well, that value over there is supposed to be X. Where are those X values? They're in L1. All right, times 0.4 to the Well, raised to the 5 minus, where's the x value going? In L1 times 0.6 to the, where are the L values? In L1. Okay, so I press enter and all that stuff comes out there. There's the 0.3456 for when x is equal to 3. You can see that right there. So this gives us our results. Get rid of that. Move this over here. This is the probability distribution for that whole thing. It should be true that we add those all up and we get 1. We can also do a stat plot of that, and this would be the graph of the probability distribution. Let's look at what that would be. So if I go to second y equals and go to the stat plot and turn that on, I want that on. Wait, I want that on. And I want my y list to be L2 because that's where it is. I want L1, L2. And I'm going to make sure that everything else, ooh, I got a lot of junk in there. Get rid of that stuff. Turn everything else off, clear it or whatever. Where's all that from? Okay, and then do zoom 9. That is my probability distribution. Probably want to have some scale on the y-axis that we aren't seeing. Maybe a scale on both sides. Go to 0. Make that, well, you don't want that to be any bigger than 1, but let's see what 1 does there for us and make this go by 0.1. See what that graph looks like. Got dots too. Let's make that window not so big. There's my probability distribution. So I'll put that over here too. And there we go. And that ends this vodcast.